All right, students. So let's commence on with our lecture. We'll be learning using these PowerPoint slides, the system of linear equations, right? So what we'll be doing in this topic, we'll be covering two variable system of linear equations and three variable system of linear equations. You know, we can call it a 2x2 system or a 3x3 system. No need to worry about what a system is or what a 2x2 system is or what a 3x3 system is. We'll understand as we go along these slides. These are the learning objectives. You, at the end of the lecture, you'll be able to determine the nature of a solution using the slope intercept form. You'll be able to determine the nature of solution using the graphical method. And then you'll be ultimately be able to solve the system of equation with two variables and then the system of equation with three variables. Now, before we commence and talk about system of linear equation, let's take a recap of linear equations. So this is an example of a linear equation with with one variable, sorry, x plus 3 equals to 10. Now you know that here the value of x can only be one number, and that is 7, right? This equation has only one solution, which is one correct solution, which is x equals to 7, right? You cannot say that my x can be 4 because 4 plus 3 is 7 and that's not 10, right? So it has only one solution. And now this is an example of a linear equation with two variables, x plus y equals to 4. Now an equation, a linear equation with two variables, it has solution sets, and these solution sets are infinite in number. For example, you can say that my x is 2 and my y is 2 as well. 2 plus 2 is 4. That makes sense. At the same time, I can also say that my x can take the value 1 and my y can take the value 3. This also makes sense because 1 plus 3 is 4. Similarly, 3 and 1 is again another solution set. 0, 4, 4, 0, 1.5 and 2.5. These are all examples. These are all examples of solution sets. And what I'm trying to demonstrate here is that these solution sets, they will be infinite in number, right? But now we're talking about the system of linear equations. What is a system? A system of equations, it is a collection of two or more equations with the same set of unknowns, or by unknowns, I mean variables. In solving a system of equation, we try to find the values for each of the variable that will satisfy every equation in the system. Now this, for example, is a system of linear equation where we have more than one equation. We have two equations, and both of these equations, they have the same variables, right? Like we have x and y in the first equation, and we have also x and y in the second equation. So this is a system of linear equation. And this is an example of a 2x2 system. What does it mean by 2x2 system? It means that there are two equations, and both of these equations have two variables in number. So you can ultimately guess that a 3x3 system will have three equations, and all of those three equations will have three variables in them. But we'll take a look at them at the later end of this course. Now you have to realize that for example, in this system, I can say that my x is 2. For the first equation, I can say that my x is 2 and my y is 2 as well. Now this x equals to 2 and y equals to 2, it satisfies the first equation, but does it satisfy the second equation, right? So in hindsight, it does not. 3 times 2 is 6, 6 minus 5 times 2 is 10, 6 minus 10 is minus 4, and we need the answer of 4, right? So 2 and 2 does not satisfy the second equation. It does satisfy, however, the first equation. What we need in a system of equation is basically the values for each of the unknowns that will satisfy every equation in the system. So such a value that will not only satisfy this equation, but also second equation as well. The equations in the system can be either linear or non-linear. However, this lecture will focus on linear equations. Now, we have a few methods for obtaining the solution of a system. We'll be studying two of them. The first one is the graphical analysis, and the second one is finding the solution using the elimination method. Now, an important thing to note is that the solution of a system can be of the following three types. We can either have a unique solution, right? Now, what does it mean by unique solution? It means that I can say that the value of x is 3 and the value of y is 1. Now, this is a case of a unique solution. I can have no solution where I do not have any solution at all, where I can say that x and y do not have any values that satisfy both of these equations, right? And then I have a case of infinite solution, where if I put x or y, where if I take any value for x and y, they will satisfy both of those equations in the system, right? So we'll be taking a look at the graphical analysis now, and we'll see how how the three solutions present themselves in the graphical analysis method. What is the graphical analysis? Now, from your previous lectures, you would have learned that a linear equation with two variables, it graphs as a straight line. So, for example, if I uh, this is my x, this is my y-axis, and this is my x-axis. Uh, if I were to draw a linear equation, it will graph as a straight line. You know, it can be like this, it can be like this, it can be like this, or whatever. But the important thing to notice is that it will be a straight line. Thus, a 2 by 2 system of linear equation will give us two straight lines in two dimensions. So basically, when I have a system of equation, if I'm saying that I have two equations, a 2 by 2 system, that means I have two equations, then that would mean that I will have two lines in my coordinate axis. And when I'm talking for a solution, when we're solving for the system, we're looking for values of the two variables which can satisfy both the equations, right? That's what we're looking for. Okay, the values satisfy the first equation as well as those values satisfy the second equation as well. That's what we're looking for, and hence graphical analysis में हम क्या कर देखना चाह रहे होते हैं? We are graphically trying to determine whether the two lines have any points in common. ऐसी कौन सा point होगा? If I'm looking for a unique solution, तो ऐसा कौन सा point होगा जो कि दोनों lines पे common होगा? Let's take a look. So, like I told you, a 2 by 2 system of equation will always have two lines, right? Two lines like this, two lines like this. This is a special case I'll discuss. So, let's take a look at one solution or unique solution. Suppose I have an equation that graphs something like this. And the second equation, it graphs something like this. Now, this point of intersection, we're basically looking for the point of intersection where the two lines meet. This point of intersection is the point where the values of x and y are common to both equations, right? This is, for example, 1 comma 2, this point. So this point is common to this line as well, and it is common to this line as well, right? So this is what we are looking for a one unique solution. If the graphs of the equations intersect, then there is one solution that is true for both equations. This is a case of unique solutions. Then we'll take a look at no solutions. What happens is, suppose if the graphs of the equations do not intersect at all. For example, if they are parallel lines do not intersect anywhere, then there are no solutions that are true for both equations. There is no point of intersection. There is no point that is common to both of these lines. So as a result, there will be no solution to the system of equation. Then we take a look at this case. If the graph of the equations are the same, then there are infinite number of solutions that are true for both equations. Suppose I plot, wait, these are my axes. Let's see. And I plot my first equation and it comes out something like this, right? And then I take a look at my second equation and then it also comes out something like this. It's coincident lines, right? So this is a case where my lines are touching each other at every point, right? So you can see that it is touching it here at every point, right? So this is a case of infinite solutions, or it's a case of coincident lines or infinite solution, right? So this is what it is. Now, before we, since this can be a bit of a hectic process, we have to draw the axes and then the lines. So in order to know whether we'll have a solution or not, or whether we'll have no solutions, or if we will have infinite solutions, we can use the slope intercept method. What is the slope intercept method? Basically, slope intercept form is y equals to mx plus k, right? I'm sure you've studied it in the previous lectures. So we compare the gradients and we compare the y-intercepts of the two lines that we have. From figure one is a case of unique solution. We studied what is figure one. This is figure one, right? So this is a case of one solution or unique solution. When we have a unique solution, when will we have a unique solution? We'll have a unique solution when the gradients of the two lines are not same, right? You can obviously see this line has a different gradient and this line has a different gradient. So whenever we have two equations, two linear equations that make up a system, and both of these equations have different gradients, then we can say clearly that this is a case of a unique solution. If you look at figure number 2, which was a case of no solutions, we can figure out if we have a case of no solution or not when we compare the gradients as well as the k, which is the y-intercept. If our gradients are same but our y-intercept is not, then this is a case of no solution. And similarly, from our figure 3, which is a case of infinite solution, if our gradients are same and our y-intercepts are same, this will be a case of infinite solution. So this is the interpretation of solution using the slope intercept method. Let's do a couple of exercises. This is exercise exercise 3.1 from page 96, and this is question number 3. We have two equations, and these two equations, they form a system of equation, and we need to solve them. I'll label the first equation as equation 1, and the second equation will be called equation number 2. So the first thing that we need to do is to convert equation 1 into the slope intercept form. How do you do that? The slope intercept form is basically y equals to mx plus k. So y needs to be the subject of the equation. Y needs to be on the left side, and on the right side we need to have the terms of x and a constant, right? So how do we do that? I'll take x to the other side. I'll subtract 4x from both sides. So what I'll get is minus 2y equals to minus 4x plus a. Again, remember, I'm considering equation number 1. Then I'll divide both of these sides by the number minus 2. Resultantly, my equation in the slope intercept form is y equals to 2x minus 4, where my slope is 2 and my y-intercept is minus 4. Now we'll do the same procedure with equation number 2, right? I'll draw a line for comparison. Then the slope intercept form of equation number 2, again slope intercept form is what? Y equals to mx plus k. I have to bring equation number 2 to the slope intercept form, which is y equals to mx plus k. Resultantly, how I can write it? I can take x to the other side, it will become negative. So 2y equals to minus x plus 12. I divide both sides with the number 2. I get this, and when I simplify, I get y equals to minus half x plus 6. Here I can see that my slope will be minus half and my y-intercept will be plus 6, right? So now we'll compare we'll compare the slopes and we'll compare the y-intercepts. The first step is to compare the slopes. The slope for the first equation is 2, right? Whereas the slope for the second equation is minus half. You can see that 2 and minus half, they're obviously different, right? They're not equal. So since my gradients, they are not equal, they're not the same, this will be a case of unique solution, right? As we discussed earlier. When will you have a unique solution? When our gradients are not the same. Now this is basically the graphical representation of this answer. 4x minus 2y equals to 8. This graphs as this line, whereas the second equation graphs as this line. And this point right here, this is the unique solution. The solution to this system of equation is x equals to 4. This is 4, right? And this is y equals to 4. So when I put the values of x as 4 and y as 4, then both of these equations are satisfied. This is how you solve a system of equation using graphical analysis. Then let's take a look. This was obviously what we studied here was a case of a unique solution. Uh, sorry. This was a case of unique solution. So let's take a look now at a case where we have no solution, right? So again, this is question number 14, same exercise, same exercise. I'll label the first equation as equation 1. The second equation, I'll call it as equation number 2, right? Again, I'll repeat the same old steps. I'll bring the first equation into the slope intercept form. Very easy to do so. I'll just take x to the other side and divide by -2. Resultantly, what I have is y equals to half x. This is my slope intercept form. You'll notice that there is no plus k. So I can just say y equals to half x plus 0, right? So my slope here will be half and my y-intercept will be 0. I'll repeat this whole procedure for the second equation again. I'll bring this to the slope intercept form. I'll take minus 3x to the other side. What I'll get is 6y equals to 3x plus 5. So simplify it, and resultantly what I get is y equals to half x plus 5 by 6. My slope from this equation is half and my y-intercept is 5 by 6. Now again, we'll start by comparing the slopes. The slope for the first equation is half and the slope for the second equation is half. Now this means that both of my lines, they have the same gradients. Now the second step is to look for the y-intercept. The y-intercept in this is 0 and the y-intercept in this is 5 by 6. The y-intercepts, the value of k or the y-intercepts, they are different in both of these equations. So resultantly, this is a case of no solution. Why is it a case of no solution? Because even though my gradients, they are the same, but my y-intercept or my k, they are not the same. K1 is not equals to K2. So this is resultantly a case of no solution. What this means is that this is the first equation. This line right here, this is the first equation, and this line right here is the second equation. You can see that both of these lines do not have any point in common. Since they don't have any point in common, there is no value of x or there is no value of y that can satisfy both of these equations. As a result, this is a case of no solution. We do not have any solution in this case. Okay. Let's move on. We have a third case to identify, and that was a case of infinite solutions, right? Again, we have question number 17, another case, label it equation 1 and 2. We'll bring equation 1 to the slope intercept form. What we'll get is y equals to 2x minus 5. Repeat the same procedure for equation number 2. The slopes for this equation will be 2 and the y-intercept will be minus 5. Repeat the same case for equation number 2. We get y equals to 2x minus 5, right? Again, if we take a look at the slope of this equation, we'll have slope will be 2 and my y-intercept will be minus 5. So what we can conclude, let's start a comparison. Let's take a look at the slopes. The slopes, they are the same, right? M1 is 2, M2 is 2 as well. The y-intercepts, k is minus 5 here and k is minus 5 here as well. You'll notice that both of these both equations, they're actually the same, right? So when we have same equations, this is a case of infinitely many solutions. Why is it a case of infinitely many solutions? Because my gradient, they are the same. M1 is the same as M2 and my y-intercept is also the same. K1 is equals to K2. This is the line, right? This is the one line. Actually, this is the first line and the second line is this one as well. They're touching each other. They're, making contact with each other at each different point. So resultantly, at each point we have a contact at this. We have infinite solutions. This is what this implies. So this was our solution by the graphical analysis. We'll move on now to determining the solution of a system of equation by using the elimination method. This is a very popular procedure for obtaining a solution. Now, if we are given a system of equation, what we do with the two equations or multiples of the two equations are added in such a way so as to eliminate one of the two variables. the resultant equation then has one variable which can be used to obtain the value for that remaining variable, and this is substituted back to get the value of the second variable. This may sound a lot of complex English and everything, but when we do it with the help of an example, you'll see that it's not much that difficult at all. I would rather explain this using this Word file right here. What is the elimination method? It is a technique for solving a system of linear equations. When we'll be walking through a couple of examples. Let's take example number 1, right? So we're asked to solve this system of equation, this right here. 2y plus 7x equals to minus 5 and 5y minus 7x equals to 12. Now you notice, first of all, that the first equation, this equation right here, has a plus 7x term, and the second equation has a minus 7x term. What we do in this elimination process is we basically add the two equations together or subtract the two equations together in such a way that one variable is eliminated, right? So we'll add the two equations. These terms will cancel if we add the equations together. That is, we will eliminate the x term, right? So how do you do this elimination process? You write the first equation as it is. Obviously, you may have to make some changes, but here we don't have to make any changes. All we have to do is add the two equations. So first equation you write as it is. The second equations you write as it is. You draw a line underneath, and then you start adding them. 2y plus 5y is equals to 7y, right? Plus 7x minus 7x will be 0. Will be 0x, and 0x is what? It's nothing but 0. And on the right side, minus 5 plus 12 equals 7, right? So what we have over here, this here, 7y plus 0 equals to 7. This again is another separate equation. And this is one equation, and we have one variable in it. So we can easily solve this equation to get the value of y. How do you do that? 7y plus 0 equals to 7, which brings us to 7y equals to 7, solving for y, and divide both sides by the number 7, we get y equals to 1. Now, when we have this value of y, we plug this value of y back into our first equation. Any of these two equations, right? I'll plug this back into the first equation right here. This was the first equation, 2y plus 7x equals to minus 5. Let me remove this. Y, the value of y is 1. 2 dot 1, that basically means 2 multiplied by 1, because I've added 1 over, substituted 1 over here. So 2 times 1 plus 7 times x equals to minus 5. 2 plus 7x minus 5. Similarly, we'll have to simplify this to get the value of x, which is minus 1. So the solution to the system of equation is x. The value of x is minus 1, and the value of y is plus 1. Now, how can we check whether the answer that we have, is it correct or not? We can check our solution by plugging these values back into the original equations, the two equations. Value of x equals to minus 1 and y equals to plus 1. If we plug into any of these equations, the equation will be balanced, any of these two equations. So let's try to plug it back into this equation number 2, which was 5y minus 7x equals to 12. 5y minus 7x equals to 12. I'll put y's value as 1, 5 times 1, minus 7 times minus 1. I calculated the x value as minus 1. So all I have to do is substitute the values of x and y into this equation, and equals to 12, question mark. The question mark here, it's telling me that is it really equals to 12, because I don't know, right? So 5 times 1 is 5. Minus 7 times minus 1 is plus 7. 5 plus 7 is 12. This equation is balanced. What this tells us is the values that we have calculated, x equals to 1, minus 1, and y equals to 1, they are correct, right? The solution checks out. So this is basically the elimination process, where you add the two equations, or you can also subtract the two equations just to remove a variable. But it is not always as simple as it is. There can be some complications. Let's take a look at the second example. We're asked to solve this system of equation, right? So first off, you'll notice that right here I have minus 9y, I have minus 7y. I can't add these two or subtract these two to give me 0y, right? So let's take a look at x. Here I have 4x, and here I have 16x. I can't add or subtract these two and that gives me 0x. So what am I supposed to do? What I can do is we can multiply the first equation by the number -4 to get an equivalent equation that has a -16 term, right? If I multiply this equation right here, if I multiply it with the number -4, what will I get? I'll get -16x here, and then I can add -16x and 6 plus 16x to give me 0x. Hence, I'll be eliminating the variable x, right? Our new but equivalent system of equation will look something like this. What's happening is I have multiplied -4 with this equation number 1, and what happens, you can't just multiply -4 with just one term. You have to multiply with each term of each equation. So -4 times -9 will 9y will be plus 36y, right? -4 times plus 4x will be -16x, and -4 times -20 will be plus 80, right? So this is the equivalent form of my first equation. And then I'll write the second equation as it is down below, -7y plus 16x minus 80, right? Now I can add these two equations so I can eliminate the x term. What do I get? I'll just write them as it is and I'll add them. 36y plus -7y, which basically means 36y minus 7y, which becomes 29y. Minus 16x plus 16x is 0. And plus 80 plus minus 80, which is 80 minus 80, it becomes 0. So what we have here is 29y equals to 0, right? Divide both sides by 29, we get the value of y as 0, y equals to 0. Now put this value of y back into the first equation, into any equation, whatever we have. What we get is, put y equals to 0 in this equation. This was our, this equation right here. 36 times 0 minus 16x plus 80. 36 times 0 is 0 minus 16x plus 80. Solve for x. We'll get the value x equals to 5. The solution to this system of equation is x equals to 5 and y equals to 0. And if you substitute x equals to y and y 5 and y equals to 0 in any of these two equations, you'll find that the equations are balanced, and this is our solution. So this is what the system, the elimination method is, right? Elimination method basically is where we have two equations and we add them, but again, I'll repeat again, we can also subtract them, but subtraction can cause some calculation errors. So it's usually better to just add the two equations in such a way so that the variables, one of the variables, it gets cancelled, and then we find the value of the remaining variable. Like for example, if I eliminate x, then I get y. I find the value of y, and then I put it back into any of these two equations, then I find the value of x, right? So I get the values of x and y. Now let's take a look at this question number 11 from your book. You'll notice right away that, the coefficients cannot be we cannot just simply add the two equations. We have 2x here and 4x here. 2x plus 4x will give me 6x. I want 0x or 0y for that matter. Minus 3y plus 2y will give me minus y. It's my y will still exist over there. So we need to make some modifications. We need to multiply something. Okay. So what we can do, I can make this 2x into 4x. I can make this 2x into basically minus 4x, right? If there was any way to make this 2x into minus 4x, and then I could add these two, right? So how can I make 2x into minus 4x? I can multiply the first equation. This is equation 1. This is equation 2. I can multiply the first equation by the number -2 and add equation 2 to it. So what happens when I multiply -2 to this equation? -2 times 2x minus 3y equals to -2 times -13. I told you we have to multiply -2 or whatever number that we're multiplying the equation with. We have to multiply them to the whole equation, all the terms. So what we get over here, -2 times 2x is -4x. -2 times -3y is plus 6y, and -2 times -13 is 26 plus 26. This is the equivalent form of my first equation. Then the second equation I'll write down as it is, right? And I'll add this to -4x plus 4x will give me 0x. I have eliminated successfully the variable x. 6y plus 2y will give me 8y, and this 26 minus 2 will give me 24. Resultantly, I can calculate the value of y. 8y equals 24, divide both sides by the number 8, and I get the number y equals to 3. Now what I'll do with this y equals to 3, I'll put this value back into any of these original equations to get the value of x, right? So put the value of y in equation number 1. I'll put it in equation 1. You can put it in equation 2 as well. 2x minus 3y equals to minus 13. Put the value of y right here. Y is value 3. आप यहाँ पे लिख दें 2x minus 3 times 3 equals to minus 13. Solve it, simplify it. You get the value of x as minus 2. So what you got, minus 2 comma 3. This is a solution set, right? And this implies a unique solution. You're getting one answer for it. You know, you're getting the value, one value for x and one value for y. This is implying a unique solution. Again, we're touching those three types of solution, you know, unique solution, no solution, and infinite solution. So this again is a case of unique solution. And the two examples we studied before, they were also cases of unique solution. Let's move on to something where we have something other than a unique solution. Let's take these two equations as a system. Now you'll notice that obviously, again, you can't just add them together to eliminate a variable. What you can do is if you want to eliminate x, you can multiply the first equation by the number 4, right? You'll get 4x over here, and then add the two equations, you'll get 0x. So let's see how it pans out. We would solve it through elimination. Multiply the first equation by the number 4 and add equation 2 to it. 4, this is the first equation, right? And I have written it as it is right down here. 4x minus 2y equals to 4 times 4, right? When you simplify this, what do you get? 4x minus 8y equals to 16. And then you have to bring the second equation right down and add those two equations, right, as it is. So 4x plus minus 4x will give me 0x, right? But at the same time, when I try to add the y terms, I'll get minus 8y plus 8y, which is 0y. And there's some number remaining here, 16 minus 10 will be 6, right? So I have basically eliminated both of my variables, 0x plus 0y, and I'm getting something as equals to 6. What it's telling me is that 0 is equals to 6. 0 can never be equal to 6, right? This is a form, this is an incorrect equation, right? This is a contradiction, in fact. So this is a case of no solution. Whenever we are working with equations and we are trying to eliminate some variables and we end up eliminating both of the variables, and we have an equation something like this: 0 equals to 6, or 0 equals to 10, or 0 equals to 2, or minus 2, whatever, you know, an equation that is basically a contradiction, a false equation. Whenever we get a false equation, that is a case of no solution. Okay, so that was a case of no solution. Let's take a look at a case of infinite many solutions. So I have these two equations. Again, you'll notice, well, first of all, I'll have to bring this second equation into the journal form, which is 3x minus 6y equals to 6, right? Now you can see that if I multiply this, multiply the first equation by the number 3, I'll get minus 3x. And if I can add the 2, I can, you know, simply just eliminate the x term. We would solve it through elimination, multiply equation 1 by 3 and add equation 2 to it. 3 times minus x, you know, we're multiplying the first equation with the number 3. What do we get is minus 3x plus 6y equals to minus 6. Then this is, remember, this right here is the equivalent form of equation number 1, right? Then we'll write equation number 2 as it is, downwards to it. And you'll notice it's pretty much the same equation, 3x minus 6y equals to 6. When you add these two equations, you'll get 0x plus 0y equals to 0, right? You'll get 0 equals to 0. Now this is not a false equation. This is a true equation, right? 0 is equals to 0, isn't it? So this is a case of infinite many solutions. I'll repeat again. Whenever during any elimination process, if I get, you know, I get something like 0x plus 0y equals to 0, you know, I can simplify it to 0 equals to 0. That is a case of infinite many solutions. If I get something like 0 equals to 10, that is a case of no solution. And if I get obviously some values for x and y, that is a case of unique solution. Okay. Now, these are some of the practice questions for you that you're all supposed to do, and their answers are mentioned in it as well. You can compare these answers and see what suits you best. In the next lecture, we'll be talking about the solution of a 3 by 3 system of equations. I'll see you in the next lecture.